exponential function of a complex variable that means we want to define something like e to the power z. Okay. So this object we want to define. Okay. Now you have been learning exponential function of a real variable for a long time. Okay. So maybe I think first time it was introduced in 11th standard, a to the power x, e to the power x, and then you learned that derivative of e raised to x is e raised to x, integral of e raised to x is e raised to x, and then in 12th standard, first year BSc calculus, you learned that it is increasing function, it is one-to-one function, exponential function is always positive, and so on. So basic properties of real exponential function you have already learned for last whatever 3-4 years. We want to now move on to exponential function of a complex variable. This definitely you have not seen before, except for a possibility that you have seen the formula of this type. Have you seen this formula, such formula? I am sure you must have seen this because it is used in physics also and maybe in some other mathematics courses or maybe first year BSc. You have done this, but then how to interpret this? Because left hand side is a to the power complex number. What is definition of such quantity? What do I mean by e to the power some complex number? Then one answer is that this is definition. Okay. But now we will define e to the power z for any z which is x plus iy. That is our objective. So take any complex number, then we want to define what is e to the power z. So suppose you have e to the power I. How do you make sense out of this quantity? We will learn, because we will define e to the power z for any value of z. So we will be able to understand this. Okay. So idea is to you define the exponential function. So there is an advantage here that if you, so this theory of elementary functions of complex variables we are starting from scratch. So from definition we are developing this. So if you understand it right from the beginning and if you keep track, keep solving problems, then you will digest the material fast, because right from the definition of these functions we are developing their properties and comparison with the real variable and things like that. So on your screen now you go through this properties of the exponential functions of a real variable e to the power x, e to the power x. So first I want to recall what is e to the power x, where x is real variable. X is a real variable. So this function, sometime also denoted by exponential function, is defined on the entire real line, but it takes only positive values. So exponential function is always positive. never takes negative values. Okay. So this is r to 0 infinity. You just look at the notes that are there in front of you, and then this property that you see on the board is also written on the notes, that it is always positive at every real number x. And further it is written there that the exponential function is invertible, and the inverse is called logarithm, and it acts on this. So this function, exponential function, is 1 1 on 2. So this is property that e to the power x or exponential, both symbols I may use, is 1 1 on to 0 infinity. That means with this domain and this codomain, it is a bijection. It is a bijection. So every 1 1 on 2 function has inverse. So this inverse is normally called logarithmic function, and then that is from 0 infinity to r. So this is inverse of e raised to x, the inverse function, inverse of exponential function. That is, if e to the power x is y, then log of y is x. It means if and only if, in fact. So in this sense, this is inverse. So inverse of the function. Okay. So exponential function is a bijection from r to 0 infinity, and its inverse is normally called logarithmic function. Actually, one needs to define one of these functions independently and then show that whichever you define. So suppose if I define log from this to this, and if I prove that this is 1 1 on 2, then its inverse I can define, this is its inverse exists, and I can say that exponential function is in the inverse. Or first of all, I need to define exponential function independently and show that it is 1 1 on 2 from r to 0 infinity, and therefore it has inverse, and inverse is called log. So one of these two can be defined in terms of the other, but one of these two has to be defined independently. Of course, I am not going to define this function, any one of these two, independently at present. Or if you want, you may just think on these lines. That is, you may define log x like this as 1 to x 1 over t dt, and show that. So this I am defining now from 0 infinity to r. So x is in 0 to infinity. So show that this function log is a bijection. And then I can say that its inverse is exponential function. Or I can define exponential function as the solution of the differential equation. So f dash equal to f with f0 equal to f dash 0 equal to 1. So there is unique solution satisfying this, and then that I can define as e to the power x. So by existence and uniqueness theorem of, this is first order linear differential equation. So it will have unique solution with reference to this boundary condition f dash 0 equal to 1, and then that unique function I can call as exponential function. and then I can show that it is 1 1 on 2 and its inverse is logarithm. So you can define one of them and then show that it is bijection and find the other one. But anyways, you keep these properties in mind, that is this function is 1 1 on 2, exponential function is 1 1 on 2 from r to 0 infinity. That means it is always positive, it never takes value 0 or it's never even negative. So it is always positive. Exponential function is always positive for all x in R. Okay. The next property that you see there is that e to the power x plus y is e to the power x into e to the power y. Okay. So e to the power x plus y is e to the power x into e to the power y. This is a very important property, and we can rephrase this as, if you consider R plus, then it's a group, it's a additive group, okay, and then I may consider 0 to infinity, that is positive real numbers. So this is group under multiplication. So this set under multiplication and R with under product, and this is group under product, group under addition, and then this function, that is exponential function, this property says that if you add two numbers here, then it is multiplication, e to the power x into it. So this is homomorphism, and further it is bijection, so it is group isomorphism. Okay, so it is written there, that is the function is isomorphism between the additive group of real numbers and the multiplicative group of positive real numbers. See, remember, this is a group because if you, so what is identity element? Identity element is 1 under multiplication. If you take product of two positive numbers, it is again positive, and inverse of a positive number with respect to multiplication, so inverse of 5 is 1 by 5, which is again in 0 infinity. So this is group under multiplication, this is additive group. So here identity is 0, inverse is negative. Okay. And these two groups are isomorphic via exponential function, that is x goes to e to the power x is the mapping. Then, so suppose phi x, phi of x plus y is phi x into phi y, like that, where phi is e to the power x. So this is e to the power x plus y, e to the power x into it. So this is group homomorphism. Plus it is bijection, so it is isomorphism of groups, these two. Okay. And then it must take identity to identity. So 0 goes to 1. So e to the power 0 equal to 1. And then e to the power nx, that is x plus x plus x n times, then it is e to the power x to the power n. For all n in Z, because inverses also exist. So e to the power minus x is e to the power x raised to minus 1, that is 1 over e raised to x. Okay, like that it is. E to the power minus 2x is e to the power x raised to minus 2, that is 1 over. So in particular e to the power minus x is 1 over e raised to x. Like that. That I am putting here what? This n equal to minus 1 I have put. You may put any integer. Still this is valid because of the group isomorphism. Or you can just inverse goes to inverse. Okay. Minus x goes to 1 upon phi of minus x is 1 upon phi x, because this group is under multiplication. Okay. Next is e to the power x goes to infinity as x goes to infinity. Okay. And e to the power x goes to 0 as x goes to minus infinity. Let us draw the graph. So e to the power 0 is 1, so it will pass through this point 0 1 and it is like this. So this is 1 and it goes to, so this is how e to the power x behaves. As x goes to infinity, e to the power x will go to infinity. Okay. In fact, it is increasing function. Since it is 1 1, and further it has this property that its derivative is itself, that is it is differentiable, and derivative of e to the power x is e to the power x. It is continuous also, because it is differentiable, it is continuous. And 1 continuous function from R to R is monotonic. Okay. 1 continuous function from an interval I to R is always monotonic. Is monotonic. Try to prove this. Take this as an exercise maybe. It is obvious, if you draw pictures it will be clear that the function is continuous and it is 1 1. So if it starts increasing it cannot come back, because then it will have two values. Okay, I mean 2 values, it will take same function value. So it won't remain 1 1. So, and then once it is monotonic, you just have to check for 2 points and then you come to know as to whether it is increasing or decreasing. So this exponential function is increasing, okay, because this logarithmic function is also increasing, and you may think like that, and inverse of an increasing function is also increasing. Okay. So exponential function is increasing. I am talking only about real variable function. Remember, I have not yet touched e to the power z, where z is complex. That I am going to define. But let us first of all revise the properties of exponential function of a real variable. So I am talking about e to the power x, our old friend, which we have been dealing with for so many years. So I am just listing for our ready reference the properties of the exponential function of a real variable. So you just see the next one, that the exponential function is differentiable and e to the power x is derivative is again e to the power x, and therefore it is infinitely differentiable. So once it is differentiable and derivative is e to the power x, then I can again differentiate and you will again get e to the power x. So suppose if I have e to the power x, if I take the derivative, again e to the power x. So if I take second derivative, also it is e to the power x. Okay, so this first derivative is same function will actually imply that if you take any nth derivative, then it is again going to be e to the power x. So this is also a remarkable property that all derivatives are again e to the power x. So it's a function whose all derivatives coincide and they are all again e to the power x. E to the power x is unique solution of the differential equation y dash equal to y with y0 equal to 1. Okay. So this is exponential function can be looked upon as a solution of a differential equation. Last year you have seen this type of differential equations, that is d minus 1 times y equal to 0. If you remember, that is dy by dx, this is differential operator, dy by dx minus y equal to 0. So then the solution is of the type e to the power x times alpha, but you want y0 equal to 1, so you want alpha equal to 1, that means e to the power x. So it is unique solution of the differential equation f dash equal to f and f0 equal to 1, as I told you. The next property is f is a real valued differentiable function on R satisfying f of x plus y is fx into fy with f0 equal to f dash 0 equal to 1, then fx is e to the power x. So this is functional equation. This is functional equation approach, that is f of x plus y is fx into fy. E to the power x satisfies this equation. If you put in place of f the exponential function, it will satisfy. And in fact, if you put conditions like f0 equal to f dash 0 equal to 1, so it is assumed to be differentiable, then it is unique function. So this implies then that fx is e to the power x. It implies that f is e to the power x. The exponential function admits power series expansion. Okay. Next property on your screen you see is that this function admits power series expansion. So this function e to the power x is 1 plus x square by 2 factorial and so on. The general term is x to the power n by factorial n and so on. And this series converges for every x in R. This in fact converges for every x in R. Once it converges for every x, it defines a function, because for certain x0 it converges to a real number. So that is image of x0. Okay. So once this is convergent, so if I just look at this series, then if it converges for every x it will give some answer, okay. That means it defines a function. So this is another way of defining e to the power x. You can define e to the power x like this. Or after having defined e to the power x in so many different ways, you can say that it admits this expansion. This is nothing but Taylor series expansion of e to the power x around 0 in the powers of x, that you call Maclaurin series expansion of e to the power x. This is also important property which when we talk about e to the power z, you will see that similar expansion with x replaced by z will also hold. Okay. So this is power series expansion. So this right hand side is called power series. So a series of the type sigma ak x power k from 0 to infinity is called power series. It's called a power series. And every power series there is radius of convergence. Radius of convergence, which is given by the formula lim sup mod a n raised to 1 over n. I am not going into all these details at present, but then surely you have done this. That is, there is a real number associated with every series, such that in the interval minus r to r, this series converges. Now in case of this series, the radius of convergence is infinity. That means this limit will come out to be 0. So this will come out to be infinity. So everywhere it converges. Okay. But corresponding to every power series, you have a domain of convergence given by the radius around a point around which the power series is developed. Okay. All right. The next property is okay. So now it says that we start with the exponential function of a complex variable. Okay. So yeah. So see first three equations there carefully. Or let you first look at this. So I will hide this part at present because you see the board now. See, now I am going to define exponential function of a complex variable here. So be alert and careful, and once for all, right from the beginning, try to understand the definition very clearly so that you are comfortable when you use exponential function of complex variable z. So see that I want the exponential function to satisfy this property. So we want the exponential function of complex variable to satisfy 1. So suppose that function is f. So the desired function has properties f of z1 z2 is fz1 into fz2. I have not yet defined exponential function, but whatever definition I give, I want that function to satisfy this, that is e to the power z1 plus z2 should come out to be e to the power z1 into e to the power z2. This f I want to define, but whatever f I define, I want this. So I am writing desirable properties, that property that I want exponential function to satisfy. I want these properties for the exponential function. Okay. Second property that I want is that better it would give back our original function e to the power x when I take z to be real x, because we already have one exponential function on the real line. So if we have this complex plane, okay, so everywhere I am going to define e to the power z, but when I take this x to be real, if I take x here, if I take x here, then that e to the power z and our e to the power x should not conflict. So we should get back e to the power x again. So this means the function fz or fx, where x is real, is our original e to the power x when x is real. We want fz to be fx to be e to the power x when x is real. And third property we want is that, like in case of R, it is differentiable everywhere in the real line. Here we want that this function f is entire function, that is, it is analytic everywhere in C. So that is what we want. So f is entire function. So these are expectations from the exponential functions of a complex variable. This is what I expect the exponential function of complex variable, that it possesses these three properties. However I want to define this, I would like that the definition should be so that it satisfies these three properties, because it has to satisfy this e to the power z1. When restricted to x, it has to give to this, and then minimum thing is we want analytic everywhere. So this is kind of minimum expectation that I keep from exponential function. Now the important thing is that if I try to find a function with these three properties, I end up getting a unique function. So I will now show that if I want these three properties, okay, from a function, then that automatically leads to the definition of exponential function. Okay. So once we do exponential functions of real variables like we did just now, we come to know that the exponential function of real variables have some properties. We pick from those properties some desirable ones, that is e to the power x1 plus x2, like that. That I want also for complex variable z. So I want e to the power z1 plus z2 equal to e to the power z1 into e to the power z2. Then I want function to be differentiable everywhere, like it was in case of real. And I want that if z itself is real, then that e to the power z is same as our original e to the power x, where that already defined, predefined function e to the power x. Okay. So these three properties I want. Now we will see that if my demand is this three properties, if I demand from a function, then only one function will result, and then that has to be the definition. So the definition will naturally follow from these three properties. Okay. Let us see how. Okay. So let's start with the properties. Okay. So let us consider z. So suppose z is x plus iy, and I want to define e to the power z. Okay. But then that is e to the power x plus iy. Now I want function to satisfy this. So I want, okay, so I want, alright, let me not write e to the power, let me write f. Okay, fz I want to define. So it is f of x plus iy. But f of addition is product. So it is fx into f iy. Do you see that? Because I want this property, f of z1 plus z2 is fz1, this property, f of z1 plus z2 is fz1 into fz2. So f of x plus iy, better it be fx into f of iy. Now f of iy will be dependent on y, and it will have suppose some real and imaginary parts. Say suppose a of y plus I times b of y. Okay. So suppose, okay, our notation there could be different, so let me write the same notation so that there is no confusion. So suppose it is gy and hy. The notation there is gy and hy, I suppose. Let me go to the next page. Yes. So fx plus y, fx into fiy. So this is, suppose this f of iy is gy plus I times hy. And what is fx? Fx is e to the power x. See in your notes also, that is also my requirement. I want fx to be e to the power x when x is real. And f of x, so suppose this is gy plus I hy. Why it is gy? Because it will depend only on y, and hy it will depend only on y. But this is complex function, so it will have real and imaginary. Fx has to be what? Fx has to be e to the power x. So what fz becomes now, if I substitute fx and fiy, therefore fz becomes e to the power x into gy plus I times hy. That is fz is equal to e to the power x gy plus I times e to the power x hy. Now look at this third property. See, I have already used first two. That is, I have written f of x plus iy. Then I have written this as product fx into fiy. Then fx equal to e to the power x I have used. And now I have this form. Now look at the third property. It is entire function I want. So I want that to be entire function means what? The real and imaginary parts must satisfy Cauchy-Riemann equations. I want this function analytic everywhere. So as we want fz to be analytic everywhere, what must happen? This u equal to, so uxy equal to e to the power x gy and vxy equal to e to the power x hy satisfy Cauchy-Riemann equations. Do you understand this? We want fz to be analytic. Remember, fz is going to be the exponential function. Do you understand our standpoint? That is, we want to define exponential function of a complex variable, but we are saying that our function f, which is going to be the exponential function of a complex variable, should have these three properties. And once we demand these three properties, I am going to show that a unique function will result, so that the definition of exponential function will follow. So now the form of fz so far is this. So once I determine gy and hy, I get the definition of exponential function naturally. So do you understand this? So now by using third, I got that this real and imaginary parts of f must satisfy Cauchy-Riemann equations. So this u is this and v is this. So da by u by da by x is equal to what? This is function of y. So when partial derivative with respect to x is what? E to the power x gy, and similarly da by v by da by x is also what? E to the power x hy. Then da by u by da by y, da by u by da by y is what? E to the power x g dash y. Because this is independent of y and this is only function of y. So its partial derivative is same as its derivative. And da by v by da by y is e to the power x h dash y. Now what are our Cauchy-Riemann equations? Dabba u by dabba x is equal to dabba v by dabba y. So I will write that. Okay. So dabba u by dabba x equal to dabba u by dabba v by dabba y. Gives what? E to the power x gy is equal to e to the power x h dash y. Remember, this is true for all xy. I am not writing that anywhere, but then this is the entire function, so Cauchy-Riemann equations hold everywhere. So this is one equation I get, and dabba u by dabba y is minus dabba v by dabba x. This is other Cauchy-Riemann equation that gives e to the power x j dash y is minus e to the power x h y. Now we saw that exponential function is never 0. Okay. So this equal to this, so I can cancel e to the power x from both sides. Okay. So therefore we get gy equal to h dash y and g dash y is equal to minus hy. So this gives what? These two equations. If I again differentiate this, see this is differentiable, this is h dash is already there. So g double dash y, which is minus h dash, but minus h dash is minus gy. So equal to minus gy. And similarly h double dash, so h dash is, so this is h dash, so h double dash is g dash, but g dash is minus hy. So h double dash also satisfies this. Now this is linear differential equation of order 2 with constant coefficients, and with initial conditions let us find on gy. So what is g of 0? What is g of 0? So g of 0 is, okay, so it is g0 here, h0, okay, but g0, remember, that means y is 0. So when y is 0, z is x, okay. So this e to the power x into 1 it has to be, and then this is 0. So h of 0 is 0 and g of 0 is 1. Okay, so g of 0 with g0 equal to 1 and h0 is 0. Therefore g dash 0 is 0 and h dash 0 is 1. Okay. So this and okay, therefore g dash 0 is equal to 0 and h dash 0 is equal to 1 from this relation, because h dash 0 is g0 but g0 is 1, so h dash 0 is 1 and g dash 0 is h0 minus h0, but h0 is 0, so minus h0 is 0. Now with these initial conditions, these differential equations will have unique solution by again the theorem on existence and uniqueness, and further we know that the solution is of the type, so gy, so by theory of ordinary differential equation, last year, second year BSc you have done, that if this type of equation, then gy is always of the type some a cos y plus b sin y. Now you put G0 is cos 0 is 1, sin 0 is 0. So A is 1, G0 is 1. I am using this. And find G dash y. So G dash y, so I will find here. So G dash y is minus A sin y plus B cos y. And G dash 0 is 0. So what is G dash 0? Put y equal to 0. So you will get B, but G dash 0 is 0. So you get A equal to 1, B equal to 0. So you get G now. So G is what? A equal to 1, B equal to 0. So Gy is cos y. Gy is cos y. So I have derived that G of y is cos y. Remember, this function is uniquely determined. You see this form here. To start with, just from the requirements, we wrote fz in this form, and now g is uniquely determined. G has to be cos y. Now similar analysis for h if I start, okay. If I start, hy also satisfies similar differential equation. So if I write hy is also a cos y, b sin y, then you will get that a is 0 and b is 1. So hy will come out to be sin y, alright. So similarly hy will come out to be sin y. In exactly same way, you find out constants by using these initial conditions, okay. So hy comes out to be sin y. So I have uniquely determined gy and hy, remember. Gy and hy I have uniquely determined. Therefore I have uniquely determined f. So f is what? Therefore fz has to be, therefore fz is uniquely determined. And fz is nothing but what? E to the power x cos y, so that is gy plus e to the power x I times e to the power x sin y. This was f, okay. Let me write here if you want in the same frame of the camera. So this is gy I have found as cos y plus I times sin y. So I can take this e to the power x outside, and then I can write cos y plus I sin y. This is my fz. But what was fz? Fz was that function which satisfies that f of z1 plus z2 is fz1 into fz2. F of x is e to the power x and f is entire everywhere. From these three conditions I have derived that f has to be this form. But our exponential functions, we want all these three conditions to satisfy. So our exponential function has to be this. We do not have any other choice. Because any function f satisfying those 1, 2, 3 I have written there on your screen, I have derived that it must be this. So our exponential function is defined like this. So define now e to the power z as e to the power x into cos y plus I sin y. So this is definition. So for z equal to x plus iy, e to the power z is e to the power x into this bracket cos y plus I sin y. E to the power x is common outside. So this part depends on y and this is e to the power x. Okay. So do you understand the relation? If a complex number is given, how to find its exponential? This is formula, this is definition. So you look at this definition for 1 minute carefully. Look at this definition. Whenever any complex number z is given, how e to the power z is defined? Just stare at that for some time. Okay. So see now, several properties of this we can derive. For example, z is 0. That means what? X is 0, y is 0. So put here, x is 0, y 0. So this is e to the power 0, 1, this is 1, this is 0. So we will get 1. So e to the power 0 is 1. Okay. So maybe for certain particular complex numbers we can find out. So maybe e to the power I times pi. Compare with this z. So what is x? X is 0. Y is pi. So this is cos pi. So let me write e to the power 0 cos pi plus I sin pi. Okay. What is cos pi? Minus 1. What is e raised to 0? 1. So this is minus 1. Sin pi is 0. Okay. I pi is 0 plus I times pi. So x is 0, y is pi. So put that in that formula. E to the power x cos y plus I sin y. Do you see something very striking here in this equation? Is this a kind of shock for you, having learned exponential function of real variable? Can you immediately recognize some difference here when we are going to the complex domain? When we are considering complex exponential function, this equation suggests that it may come out to be negative. So e to the power some complex number may come out to be negative, where our e to the power x was always positive. Our exponential function was always positive. So the differences have started emerging now. So be careful. Be careful. There will be some similarities and there will be some differences. So you have to be alert. See this equation. E to the power some complex number is negative. So exponential function of a complex variable may take negative values. In fact, we will see that it will take all negative values. It can take all negative values. Okay. Except 0, it will take all values. We will see that. All right. Now, directly from the definition, what follows? Okay. So let's see the properties one by one as listed in your notes which are there. So now this definition is forced on us. So this definition I have written there, that is fz is e to the power x into cos y plus I sin y. That is definition of e to the power z. the domain of the definition is entire complex plane. So this e to the power z is defined on whole of complex plane. So this exponential function is defined from C to C, whole of complex plane. So its domain is C, codomain is C. We will see that it will not take 0 values, but it takes all other values. So you may take any complex plane here, complex plane, except this point it will assume all the values. So you may take this, then for some z, e to the power z will be that. Okay. What is real part of this function? So e to the power z, if we want to express as uxy plus I times vxy, so uxy plus I vxy, we have found it like that, it is readily there. So it is uxy is nothing but what? E to the power x cos y, and vxy is what? E to the power x sin y. So real and imaginary parts are these. Real and imaginary parts of e to the power z are like this. So uxy is this, vxy is this. Okay. Needless to say that they will satisfy Cauchy-Riemann equation, because we have found this so that they will satisfy. But let's check. Dabba u by dabba x is what? E to the power x cos y. Dabba u by dabba y is what? This is dabba, this is u. So dabba u by dabba y is minus e to the power x sin y. Dabba v by dabba x, this is v. So e to the power x cos y, e to the power x sin y, and dabba v by dabba y, dabba v by dabba y is e to the power x cos y. So dabba u by dabba x is dabba v by dabba y, and dabba u by dabba y is minus dabba v by dabba x. So Cauchy-Riemann equations are satisfied and at all points, and these functions u and v are differentiable everywhere. This is the exponential function. This is our trigonometric function of real variables. As functions of real variables, they are very nice. They are infinitely differentiable. So, and further they satisfy Cauchy-Riemann equations. So what happens? This e to the power z is the entire function. If the functions u and v are differentiable and if they satisfy Cauchy-Riemann equation, then we know that the resulting function f is what? Analytic. So e to the power z is the entire function. What is mod of e to the power z? So it is e to the power x cos y plus I times e to the power x sin y. So mod, how do you find? uxy square plus vxy square square root. So e to the power 2x cos square y plus e to the power 2x sin square y, u square plus v square square root, positive square root, that is e to the power x. So mod of e to the power z is e to the power x. Actually it is in the polar form kind of thing. So this is the absolute value, this is argument. So argument of e to the power z is y, but then let me write capital A, that means principal argument, where minus pi less than y less than or equal to pi. So principal argument. If you want any argument is then y plus 2n pi. You may add to the argument, you get again the argument. Okay. So mod of exponential function is e to the power x and argument is y. Okay. Now this is most important, that is the absolute value is e to the power x and argument is y. We will capitalize on these two observations next time and then see the geometry associated with this mapping, which is exponential function. So suppose this is complex number that you are thinking of in the plane, then this is x, this point is x, this length is x, and then this is y. Now e to the power z will have this as what? Absolute value. So it will lie on that circle of this length. And it will have this as argument. So it will make angle y radians with the positive x-axis here. So this geometry we are going to see next time, and all the properties that I have listed we are going to prove next time. So next time we will take up the task of understanding the exponential function of a complex variable in more detail, and then define other functions like trigonometric functions like sine function, cos function, and so on. Okay. So you already have these notes with you. So before the next lecture, perhaps you may go through this. You may go through all the remaining properties that I have listed of the exponential function. There are different properties that I have listed, maybe 50 odd properties I have listed. So you may go through these properties, and then we will come back to this and see the geometry also associated with these mappings. There are some differences, like I have pointed out that it can take negative values. There will be some other striking differences that we want to point out. All this we will do next time. So exponential function of complex variable, again we will come back to that and study the properties in detail next time. Till then,